In this video, we will go through some practice problems for algorithms. So the first problem here is asking us to figure out a relationship between square root n and n to the power sine n. Notice that square root n is actually the same as n to the power half, and we need to figure out whether this belongs to, let's say, so we're starting with the first option here, whether this belongs to big O of n to the power sine n. Okay, so recall, by definition of big O, to prove that this is true, we need to basically figure out a constant c and a constant n0 such that for all values of n greater than equal to n0, n to the power half should be smaller than or equal to c times n to the power sine n. Now let's think about whether any such value of n0 and c exist, right? So recall that sine n, this value here, this basically keeps oscillating between -1 to +1. Okay, so there is no such value of n0 for which no value of n0 such that for all values of n greater than n0, the value of this exponent would definitely be greater than half. Okay, and therefore it is not possible to find such a c or such an n for which this condition is going to be true. Okay, and so hence we can safely conclude that option A cannot be correct. Now notice that with the same reasoning, it is not possible to find appropriate values of c and n to satisfy any of the remaining options either. The main reason being that the value of sine n continuously keeps oscillating in this range -1 to 1. So it is not possible to ensure that for some value of n greater than n0, the right hand side would definitely be greater than half or smaller than half or equal to half. Okay, and hence the answer to this question is none of these. N to the power sine n is neither big O nor little o, nor little omega, nor big omega, nor theta of n to the power sine n. There is no relationship. The second question over here is asking us whether 2 to the power n plus 1 is equal to big O of 2 to the power n, right? So once again, from the basic definition of big O, we need to find a constant c and a value n0 such that for all values of n greater than equal to n0, 2 to the power n plus 1 should be smaller than or equal to c times 2 to the power n. Okay, now notice that if we substitute this c is equal to 2, this right hand side basically becomes 2 into 2 to the power n, which is basically 2 to the power n plus 1 itself, right? So for c equal to 2, it is possible to satisfy this inequality, right? And therefore it is correct to say that 2 to the power n plus 1 belongs to big O of 2 to the power n. The third problem here is asking us to prove that n factorial is little omega of 2 to the power n. So by definition of little omega, we essentially need to prove that limit n tends to infinity, 2 to the power n divided by n factorial should be equal to 0. Okay, so let's try to do this. Essentially 2 to the power n divided by n factorial is 2 into so on n times, divided by n into n minus 1 into n minus 2 and so on up to 2 into 1. Okay, so these are the last two terms. So if we factor these terms out and separate this product in the numerator and the denominator, we basically get 2 divided by n multiplied by 2 divided by n minus 1 and so on all the way up to 2 divided by 2 multiplied by 2 divided by 1. Okay, so notice that as n tends to infinity, basically these terms 2 divided by n, this will turn to 0, right? Similarly this will also tend to 0, and in here towards the end you will get 2 divided by 1, which is 2, and this term would be 1, right? So we are basically multiplying 0 to a value here that is less than equal to 2, right? And therefore this product should be equal to 0 as n tends to infinity. Okay, so essentially this basically shows that limit n tending to infinity, 2 to the power n divided by n factorial is equal to 0, which means n factorial belongs to little omega of 2 to the power n. Alright, so this problem is asking us to arrange the given functions in increasing order of growth rate, right? So the function with the smallest growth rate should go first and so forth. So notice that log of n factorial, right? This is, we know that this is theta of n log n. Log n factorial, this is actually omega of n cube, right? So little omega, so this actually grows faster than n cube. Square root of log n, recall that this is actually even smaller than log n, right? And n log n is obviously theta of n log n, it grows faster than order of n, right? So based on this, we can see that the smallest function we have here is this log square root of log n. Actually this log of n factorial and n log n, these grow at the similar rate, and omega and basically this log n factorial, this would grow the fastest. So the functions, the correct arrangement would be square root of log n followed by let's say log of n factorial followed by n log n. Now these two are similar growth rates, and this finally followed by log n factorial. All right, so here's the recurrence that we want to solve. Now first of all, notice that here inside the bracket this -2, this is a constant term which is not going to affect the complexity of the final or the overall recurrence. So we can actually simplify this recurrence to and write it as 3 times t of n by 3 plus n by 2, and we just need to solve this recurrence. Now this is in the form of divide and conquer recurrences, so you can actually directly use the master theorem to figure out that this is theta of n log n. But here let's try to solve this iteratively. So we have Tn is equal to 3 times t of n by 3 plus n by 2. Now as usual, let's try to expand this t of n by 3 by substituting n by 3 in this recurrence. So this would be 3t of n by 3 square plus n by 3. So let's now substitute this back here. So our recurrence equation becomes, so this is the same as 3 square t of n by 3 square plus n by 2 plus n by 2. So there is a pattern here. As you can see, the ith term would look like this. You have 3 to the power I t of n upon 3 to the power I plus I times n by 2. Now for what value of I would this n upon 3 to the power I go down to 1, right? So that happens for I is equal to log to base 3 of n. So let's substitute I is equal to log to base 3 of n here in this expression. So basically we get t of n is equal to 3 to the power log to base 3 of n t of so n upon 3 to the power log to base 3 of n. This term will reduce to 1, and we have plus so let's write it here. We have plus log to base 3 of n times n by 2. Okay, so notice that this 3 to the power log to base 3 of n, this is the same as n, and this term will reduce to 1, and here we have basically this is n by 2 times log n, right? So this entire expression is essentially n plus n by 2 times log n, and which is basically simply theta of n log n. Alright, so here is another recurrence we want to solve using iterative method. So notice that this can be rewritten as square root n is basically n to the power half. Let's now expand this t of n to the power half by substituting in the recurrence. So we get t of n to the power half is equal to t n to the power 1 by 2 square t of n to the power 1 by 2 square plus n to the power half. Substitute this quantity back here in the recurrence, so we get t of n is equal to n to the power half outside the bracket, and inside we have n to the power 1 by 2 square t of n to the power 1 by 2 square plus n to the power half this, and then outside the bracket we have plus n. So if we open the bracket, this becomes, so you see that these two powers, right, this n to the power, this power and this power, they will add. So we get n to the power 1 by 2 plus 1 by 2 square t times n to the power 1 by 2 square plus, now once again this n to the power half and this n to the power half will add, so we'll get simply n to the power 1. So this is half plus half, which is simply 1 plus n. So continuing in this fashion, the ith term would look like this. You have n to the power 1 by 2 plus 1 by 2 square plus so on up to 1 by 2 to the power I multiplied by t of n to the power 1 by 2 to the power I, and plus here you will have I times n. Okay, so now the question is, for what value of I would this term inside the bracket here in the recurrence would go down to 0 or 1, right, very close to 0 or 1, some small constant. So notice that just as this series n by 2, n by 2 square, n by 2 cube, and so on, right, upon n to the power n upon 2 to the power I, this has log n terms. Similarly, this series n to the power half, n to the power 1 by 2 square, and so on up to n to the power 1 upon 2 to the power I, this has roughly log of log n terms before this last term goes down to 1 or 0, so some small constant. So essentially substituting I is equal to log of log n in this recurrence relation, we get the left hand term becomes, so this first term here becomes n to the power half plus 1 by 2 square plus so on up to 1 upon 2 to the power log n, and here we have t of, this will reduce to 1 or some small constant, and here we will have n multiplied by log of log n. Okay, so now what is the complexity of this recurrence? That would depend on the complexity of this polynomial term here, n to the power 1 by 2 plus 1 by 2 square plus so on up to 1 upon 2 to the power log n. Now notice that this series that we have in the exponent, this is actually a geometric series which is a converging geometric series. So the sum of this geometric series would actually be less than equal to 1. Okay, even if there were infinite terms here, which there are not, there are only 2 to the log n terms. So even if there were infinite terms, the sum of the series cannot be any more than 1. Okay, so the maximum value of this term here can be n. Right, now clearly this n times log n is greater than n, and therefore this recurrence over here, this is actually big O of n log n. Alright, so this problem is asking us to solve these recurrences using the master method. So once again, we basically have to figure out the value of a, b, f of n, and n to the power log 2 base b of a, right? So in the first question, this is our a is 9, b is 3, f of n is basically log n, and n to the power log 2 base b of a in this case would be n to the power log 2 base 3 of 9, which is simply n square. Okay, now clearly n square is greater than, it grows greater than log n, and basically this implies this is the first case in the master theorem, and therefore our recurrence t of n should be big O of n square, or basically theta of n square, sorry. Okay, so this is the first question, the result for the first question. In the second question, a is 8, b is 4, and f of n is actually n square root n. So here n to the power log 2 base b of a is basically n to the power log 2 base 4 of 8, which is actually 1.5, right? So log to base 4 of 8 is 1.5, so this is basically n to the power 1.5. Now notice that this n root n is the same as n to the power 1 plus half, right? So this is also actually n to the power 1.5. So it turns out that f of n is the same as n to the power log to base b of a. Okay, and therefore the second case 2 of master theorem applies, and this implies that our recurrence t of n belongs to theta of n to the power 1.5 log n, right, which is basically the same as n root n log n. In this problem we have to use mathematical induction to prove that n factorial is greater than 2 to the power n. So let's start with the base case, right? So for n equal to 4, we know that we know that 4 factorial is basically 4 multiplied by 3 into 2 into 1, which is basically 24, and 2 to the power 4 is basically 16, right? So clearly we have 24 is greater than 16, therefore n factorial is greater than 2 to the power n for our base case. Okay, now the next is our induction hypothesis. So let's assume that n factorial is greater than 2 to the power n for some value of n. Okay, greater than, for some n greater than equal to 4. Now in our inductive step we need to prove that that n plus 1 factorial is also greater than 2 to the power n plus 1. Okay, so let's start from our inductive hypothesis here, right? So we have this inductive hypothesis, so we know from that hypothesis that n factorial is definitely greater than 2 to the power n. Now let's multiply both the sides with n plus 1, right? So if we do that, n factorial into n plus 1 should also be greater than 2 to the power n multiplied by n plus 1 from our inductive hypothesis. So notice that n factorial into n plus 1 is actually simply n plus 1 factorial. Okay, and this should be greater than 2 to the power n multiplied by n plus 1. Okay, let's remember this as our first result. Now let's again go back to our inductive hypothesis, and this time instead of multiplying both sides with n plus 1, let's multiply both sides with 2, right? So n factorial into 2 and 2 to the power n into 2, right? So 2 to the power n into 2 is basically 2 to the power n plus 1. Okay, now basically this means 2 times n factorial should be greater than 2 to the power n plus 1. Let's remember this as our second result. Now let's focus on this term on the right hand side of the first result and the left hand side of the second result. Notice that for n greater than equal to 2, this n plus 1 is always greater than 2. Okay, so what that means is for n greater than equal to 2, 2 times n factorial would be so let's do this, so let's do this the other way, right? So 2 times n factorial would be less than 2 to the power n multiplied by n plus 1, right? So in other words, from 1, this 1 and 2, we know that n plus 1 factorial is greater than 2 to the power n times n plus 1, right? And from here we know that this value is greater than 2 times n factorial, and this second result here tells us that 2 times n factorial is greater than 2 to the power n plus 1. Okay, so this implies that n plus 1 factorial is greater than 2 to the power n plus 1, hence proved. A similar proof for this result is also given over here on this slide. Alright, let's now prove that 6 to the power n minus 1 is divisible by 5 using mathematical induction. So once again, start with the base case. For n is equal to 1, 6 to the power 1 minus 1 is basically 5, and obviously 5 is divisible by 5, so the base case is true. Let's assume as inductive hypothesis that for some n, 6 to the power n minus 1 is divisible by 5. So what that means is 6 to the power n minus 1 is equal to 5 times some k, some constant k. Okay, so this is our inductive hypothesis. And now for the inductive step, we need to prove that 6 to the power n plus 1 minus 1 is also divisible by 5, which basically is by 5. Okay, so basically it would be of some form 5 times k prime. Okay, so 6 to the power n plus 1 minus 1, this can be written as 6 times 6 to the power n minus 1, which is basically the same as, so taking 6 common out, this is same as 6 times 6 to the power n minus 1, and then obviously when we open this bracket we get minus 6. So to restore the balance as in the previous step here, we have to add a 5 here. Now notice that from our inductive hypothesis here, 6 to the power n minus 1 is already a factor of 5. So we can write this as 5 times some constant k. Okay, so this equation here, this can be written as 6 multiplied by 5k from our inductive hypothesis plus 5. Now from this expression we can take 5 common out, so we get 5 times 6k plus 1. Now clearly this term is divisible by 5, right, because there is a 5 over here, and therefore this proves our hypothesis. The same proof is also outlined here. So here we have a linked list that is sorted, and we need to figure out the average number of comparisons for searching elements in this linked list, assuming that every time we search an element it is always found in the linked list. And the second important assumption is all the items are equally likely to be searched, so there are no items that are more popular than others. So more specifically, here is the problem. We are given a linked list, let's say that is storing all the elements in sorted order. So this is, let's say, element 1, this is element 2, this is element n by 2, this one is element n by 2 plus 1, and this is where our mid pointer is pointing, and this is the last element, which is n by 2 plus n by 2 equal to n. We are assuming that n is even. Okay, so this is our mid pointer. Now the way the searches work is, let's say the items are sorted in ascending order, so increasing in the towards the right. So the way the search works is, whenever we are looking for an item, we'll first check this middle element. If the item is found here, it is simply returned and no further search is needed. If the item is not found here, then we compare it with the element stored here, right? If the item we're looking for is less than the element at the mid pointer, then we search the left half of the list. Otherwise we continue towards the right of the list, right? So that's basically the summary of the search. And now we have to figure out, for searching all the n elements, what is the exact average number of comparisons that would be made. Okay, so let's think about what is the number of comparisons for searching each of these items. So if the item that we are looking for is found here at the mid pointer, right, in that case there was exactly one comparison. If the item was not found there, and let's say you find the item here at location n by 2 plus 2, then there were two comparisons, right? So first at here at the mid, and then the second was here, right? So there were two comparisons. And likewise for subsequent elements all the way up to this last element n, there will be n by 2 comparisons if the item is on the right hand side of this linked list. As opposed to this, if the item is on the left half, then again we are going to first compare the search key to the middle element. That will be one search. And now if the element that we're looking for was, let's say, here the first element, then we have two comparisons, right? So the first comparison was to this middle element, and then the next comparison was to this element, the number 1. If the item that you're looking for was, let's say, this second element stored over here, then you will first check the middle element, then you will check this first element, and then you will check the second element, right? So there will be 1 plus 2 comparisons. And likewise all the way up to this n by 2th element, there would be 1 plus n by 2 searches here for the n by 2th element. Okay, so the total number of comparisons would be simply the sum of all these comparisons, right? So for the left half, the total number of comparisons would be 1 plus 1 plus 1 plus 2 plus 1 plus 3 plus so on all the way to 1 plus n by 2. Okay, which is basically, so you notice that there are n by 2 ones here, so we can take this out, and some of these would be simply n by 2, and then we have this series 1 plus 2 plus 3 plus so on up to n by 2. So this is the left half, the total number of comparisons in the left half, and the total number of comparisons for items that are found in the right half is given by simply 1 plus 2 plus 3 plus so on up to n by 2. Okay, so we can get the total sum by simply using the result for the sum of first n numbers. We know that uh, so we know that the sum of this series 1 plus 2 plus 3 and so on up to n, this is given by n into n plus 1 divided by 2. So in this case, just substitute this n, instead of n you have n by 2 here, right? So substituting the value of n by 2 here in the series, we get the sum of this right hand side series would be n by 2 n by 2 multiplied by n by 2 plus 1 divided by 2, and the sum of the left hand side series would similarly be, so for the left hand side series we have n by 2 plus n by 2 multiplied by n by 2 plus 1 divided by 2. Okay, so the total number of comparisons would be given by this comparisons in the left hand side plus the comparisons in the right hand side. Okay, so that would be basically n by 2 plus 2 times n by 2 into n by 2 plus 1 divided by 2. So this 2 and this 2 cancels out, so we are just left with here we are left with n by 2 plus n by 2 into n by 2 plus 1. Okay, now this is the total number of comparisons, right? So to figure out the average number of comparisons per search item, we basically have to compute average as the total number of comparisons divided by number of items. Okay, so in this case the total number is this, and the number of items is simply n. Okay, so we divide this expression, let's use another color, so we divide this expression n by 2, so let's divide this by 1 by n, right? So 1 by n multiplied by n by 2 plus n by 2 into n by 2 plus 1. So basically this n and this n and this n cancels out, so you are simply left with n by 4 plus 1. So this is our final answer. The solution is also summarized over here, and this is the answer. For this problem, assume that you are in a moving business and you have a truck. The maximum capacity of your truck is weight W. It cannot carry more than W weight at any point in time. You are provided a bunch of boxes that are numbered 1, 2, 3 all the way up to n. So you want to move all these boxes in your truck, and assume that all the boxes cannot fit simultaneously in the truck, so you will have to make multiple trips. What you want to make sure is you make minimum number of trips while transporting these boxes, just so as to minimize your fuel costs. While doing that, there are two important constraints that you must satisfy. So first, at any point in time, your truck should not be carrying more than weight W. That's the capacity. That's the first constraint. And the second constraint is the boxes are numbered, and to avoid any misplaced boxes or lost boxes, these boxes need to be delivered in sequence. So what that means is, if in a given, so let's assume the first trip, right? So in the first trip, if the highest numbered box that you are delivering is k, then you must deliver all the boxes that are less than k as well, right? So 1 2 all the way up to k. You cannot, for example, mix and match. So you cannot do, let's say, 1 2 box number 1 2 and then maybe you skip 3 and 4 and then you deliver 5 6 and so forth, right? This is not allowed. All the boxes must be delivered in sequence. So this was the first trip. Now in the second trip, because you've already delivered up to boxes k in the first trip, so you will start from k plus 1, k plus 2, k plus 3, and so on up to some k plus l value, right? And so forth. Now here is a greedy algorithm to deliver the boxes while minimizing the total number of trips. So essentially this is a very simple algorithm. What it says is load the truck with as many boxes as possible before sending it out. So simply load as many boxes in sequence as possible until the truck doesn't go over its capacity. So for instance, let's say you loaded boxes 1 2 3 all the way up to k. Now if you load this k plus 1th box, the truck goes over capacity, so you send all the boxes from 1 to k, right? You don't send k plus 1th in this trip. In the next trip you will send k plus 1, k plus 2, and so on up to some value k plus l, such that if you were to add k plus l plus 1, then the truck will go over capacity, so you cannot send this, right? So this is how the greedy algorithm works. Simply load the truck with as many boxes in sequence as possible before sending it out. In this problem, we basically need to prove that this greedy algorithm is optimal. And the way to do that is we first prove that this hypothesis is true. So here is some notation. Let's assume that our greedy algorithm comes up with trips g1, g2, g3, and so on up to gk, right? And let's say there is some other optimal algorithm that comes up with trips o1, o2, o3, and so on up to some om, some m number of trips. Let's further assume that we have some function b of t such that b of t is the highest number box that was sent on trip t. So basically, if you say b of gi, this will give you the highest number box that was sent by the greedy algorithm in the ith trip. Similarly, b of OI will tell us the highest number box that was sent by the optimal algorithm in the ith trip. Okay, so this hypothesis is basically saying that for all I less than equal to k, so notice that greedy algorithm has k trips. So for all I less than equal to k, b of gi is always greater than or equal to b of oi, right? So basically what it is saying is the highest number box that is sent by the greedy algorithm in the ith trip is always either greater than or equal to the highest number box that is sent by the optimal algorithm in the ith trip. So this is the hypothesis. In part A we have to prove that this hypothesis is correct, and in part B we'll be using this hypothesis to prove that the greedy algorithm is optimal. We can prove this using induction. So recall that in the greedy algorithm we came up with a set of trips g1, g2, so on up to gk, and the optimal algorithm also came up with a set of trips o1, o2, and so on up to om. So here for the base case of induction, this is the base case, we will just focus on the first trip. So recall, in the greedy algorithm basically packs the truck with boxes in sequence until no more boxes will go in, right? So it will basically load box 1 2 3 and so on up to k, such that putting box number k plus 1 will overload the truck. Okay, so the maximum boxes that can go on the first trip is only the up to k boxes, and by definition obviously even the optimal algorithm cannot do better than this. Even the optimal algorithm can also load the truck with maximum k boxes. It cannot load the k plus 1th box, otherwise the truck would be overloaded. Okay, so for the base case this hypothesis is satisfied. The highest number box that is sent by the greedy algorithm is greater than or equal to the highest number box that is sent by the optimal algorithm. Now let's assume that our induction hypothesis is true for some trip I minus 1, right? So we'll assume that the highest box number that is produced by the greedy algorithm in trip I minus 1 was greater than or equal to the highest box number that was sent by the optimal algorithm in trip number I minus 1. Okay, so this is our induction hypothesis, and now in the induction step we need to prove that the largest number box that is sent by the greedy algorithm in the ith trip would be greater than or equal to the largest number box that is sent by the optimal algorithm in the ith trip. So let's think what the greedy algorithm will do in the ith trip, right? So in the previous iteration, that is I minus 1th trip, the greedy algorithm has already sent boxes up to b times b of gi minus 1, right? These many boxes up to this number the greedy algorithm has already sent. So in this ith trip, it will start sending boxes from b gi minus 1 plus 1 plus, and then it will next send b of gi minus 1 plus 2 and so on. The largest box number that it will send would be b times g of I. Okay, and after this the truck would be at capacity such that loading the box b gi plus 1 would make it overload. Okay, so this box cannot be loaded. Now let's think about what the optimal algorithm will do in the ith trip. So the optimal algorithm in the previous trip sent boxes up to b of oi minus 1. Now from our inductive hypothesis we know that b of oi minus 1 is less than or equal to b of gi minus 1. Okay, so what this means is this optimal algorithm still needs to send all these boxes that the greedy algorithm is sending, starting from b of gi minus 1 plus 1 to b of gi. So the optimal algorithm will also have to send all of these boxes, and to beat the greedy algorithm it will additionally need to send at least one more box, right? So basically it will need to send b of gi plus 1, this box. However, this is not possible because we have seen when we are talking about this greedy algorithm that fitting b of gi plus 1 along with boxes from b of gi minus 1 plus 1 all the way to b of gi will make the truck overload. Okay, and therefore even the optimal algorithm will either send at max b of gi boxes up to this number or fewer boxes. Okay, so this basically proves that b of gi is greater than or equal to b of oi for any ith step. So this basically proves our hypothesis. Let's now come to the part B. In part B, we want to prove that the greedy algorithm for filling the truck is optimal, right? So recall that this greedy algorithm came up with a solution with trips, let's say G1, G2, G3, so on up to GK. And the optimal algorithm came up with the trips O1, O2, O3, and so on up to OM, right? So for some numbers M and K. Now here we can use proof by contradiction because we have already proved the hypothesis in the previous part. We can prove this part using contradiction with the help of our hypothesis. So let's assume that the optimal algorithm is actually better than the greedy algorithm. So what that means is the optimal algorithm should be able to ship all the packets from 1 to n in fewer number of trips as compared to the greedy algorithm. So what that means is m should be less than k in this case. So if m is the last trip for the optimal algorithm, this means b of o of m, the highest numbered box that is sent in the mth trip by the optimal algorithm should be equal to n, the last box, nth box. So recall that we have these boxes numbered 1, 2, 3 and so on up to n. So the last box numbered n must be sent in the mth trip by the optimal algorithm. Similarly, if k is the last trip of the greedy algorithm, then the highest box number that is sent by the greedy algorithm in the kth trip should be equal to n. This means that the highest box number that the greedy algorithm sent in its mth trip, because notice that m is less than k, in its mth trip was less than n, it was not the highest box number. Now this is a contradiction. These two statements are a contradiction to the hypothesis that we just proved, right? So we just saw that for all values of I, b of gi should be greater than or equal to b of oi. Okay, so this means it is not possible that if b of o of m was equal to n, then b of g of m cannot be less than n. Okay, so therefore we see by contradiction that the greedy algorithm must produce an optimal solution. So in this problem you are given a sequence of n songs. So let's assume that your songs are uh, song 1, 2, 3 and so on up to n songs. Each song has a length. So for example, song 1 is L1 minutes long, song 2 is L2 minutes long, and so on up to song n is Ln minutes long. In addition to the songs, you are also given a group of or a set of CDs. The CDs are also numbered, so you have CD1, CD2 and so on up to, let's say, CDK. Each CD has a finite capacity, right? So each CD can only hold maximum m minutes of songs. Okay, so you are required to write all these songs on these CDs. The objective you would like to achieve is you want to minimize the total number of CDs that are used for writing these songs. Now while doing this, there are a few important constraints that must be satisfied. So first of all, the songs must be ordered, right? So they must be ordered in the specified order. So what that means is you should write the songs in the CDs in this order. You should first write song number 1 followed by song 2, then 3 and so on up to n. Okay, you cannot change the order. And an implied meaning here is also that the CDs must be ordered too. So you can, this is not going to change the complexity of the problem. So let's assume that you will first write in CD1. When you run out of CD space in CD1, then you will use CD2 and so on up to however many CDs you need. Okay, so that's the first constraint here. The second constraint is all the songs must be included, right? You cannot omit songs. And the third important constraint is you cannot split songs across multiple CDs. Okay, so if you run out of space, let's say on one of the CDs you wrote songs up to some number I, and now you still have remaining space, but the I plus 1th song doesn't fit in the remaining space, then you should use a new CD. You cannot split the I plus 1th song across two CDs. So these are the three important constraints. Now here is a greedy algorithm for satisfying these constraints and achieving the objective. So the algorithm is actually very simple. Simply put as many songs in sequence starting from song number 1 onto the first CD as possible without exceeding its capacity of m minutes. And when you run out of capacity on this first CD, you then recurse with remaining songs on the second CD and so forth. So basically you will put songs, let's say 1, 2, 3 so on up to some number I, such that putting the I plus 1th song on this CD1 will exceed the CD capacity, right? This will exceed the m minutes capacity limit. Okay, so you'll only put songs 1 to I on CD1, right? And then you will recurse on the remaining CDs. So this is the greedy algorithm, and in this problem we basically have to prove that this greedy algorithm is optimal for this problem. So once again we can actually use proof by induction, very similar to what we have done in the previous problem. Let's assume that our CDs are numbered from 1 to so on up to n. Let's assume that our greedy solution uses k CDs and there is an optimal solution that uses m CDs. Okay, so the greedy solution, for example, puts G1 set of songs on CD1, then G2 set of songs on CD2 and so on up to GK on the last CD, and the optimal solution puts O1 set of songs on the first CD, then O2 set of songs on the second CD and so on up to OM set of songs on the mth CD. Let's again assume that we have a function bt that basically gives the highest numbered song in CD T, right? So for example, if you say b of g of I, this will give us the highest number song that was written by the greedy algorithm in its on CDI. Similarly, if you say b of o of I, this will tell us the highest number song that was written by the optimal algorithm in its in CDI. Now again, our hypothesis here is that the highest number song that is written by the greedy algorithm in CDI is always going to be greater than or equal to the highest number song that was written by the optimal algorithm in CDI for all values of I less than equal to k. Okay, so let's again use proof by induction. So our base, this is our base case, right? So for the first CD, so recall that the greedy algorithm produces this sequence G1, G2 and so on up to GK, right? And the optimal algorithm has produces O1, O2 and so on up to OM. So for base case we are just focusing on this first solution here of the first CD here. So recall what the optimal solution I'm sorry, what the greedy solution would do to fill this CD1. Essentially the greedy solution will keep writing songs into the first CD until a value k, or let's say this is some value I, such that writing the I plus 1th song will exceed the CD capacity. Okay, so basically you will just write the first I songs in using this greedy solution in the first CD. Now notice, by definition even the optimal solution cannot do any better, right? So to beat this greedy solution, the optimal solution will have to write songs from 1 to I plus 1, but because writing this I plus 1 exceeds the CD capacity, even the optimal solution can at most write I songs. Okay, so for our base case, B of G1 is greater than or equal to B of O1. Okay, so this is true. Now let's assume that our inductive hypothesis is for some I minus 1 CD, the number of songs that were the highest number song that was written by the greedy algorithm was greater than or equal to the highest number song that was written by the optimal algorithm in the I minus 1 CD. Okay, now we have to prove that even for the ith CD, the highest number song that is written by the greedy algorithm is greater than or equal to the highest number song that is written by the optimal algorithm there. So from our inductive hypothesis, we know that B of Gi minus 1 is greater than or equal to B of Oi minus 1. This is our inductive hypothesis. So let's now see what the greedy algorithm will do in the ith iteration, right? So in the I minus 1th iteration, the greedy algorithm wrote songs up to number B of Gi minus 1. Okay, so in the ith iteration, in the ith iteration basically the greedy algorithm will write songs starting from B of Gi minus 1 plus 1, then B of Gi minus 1 plus 2, and so on all the way up to B of Gi, such that adding B of Gi plus 1, this song will exceed the CD capacity. Okay, so in the ith iteration, this is the set of songs that the greedy algorithm will write on CDI. Now let's see what the optimal algorithm can do for CDI, right? So the optimal algorithm for CDI will write songs starting from B of OI minus 1 plus 1, right? So basically the next song after this one. Now we know that B of OI minus 1 is less than or equal to B of GI minus 1. So what that means is to beat the greedy algorithm, the optimal algorithm will still have to write songs that start from that are contained in this set B of Gi minus 1 to B of Gi minus 1 plus 1 all the way to B of Gi, and then to beat the greedy it will have to write one more song at least, which is basically this last song B of Gi plus 1. Now from this previous discussion we know that it is not possible to write all of these songs on the ith CD because it will otherwise exceed the capacity of the CD. So this basically proves that even for the ith iteration B of Gi, the highest song number that is written by the greedy algorithm in ith CD is going to be greater than or equal to the highest song number that is written by the optimal algorithm on the ith CD. So this basically proves our hypothesis. Now we will use this hypothesis to prove that the greedy songwriting algorithm is actually optimal. So here we can again use the proof by contradiction. So let's assume that the optimal algorithm can beat the greedy algorithm. So what that means is if the greedy algorithm produces the solution G1, G2 and so on up to it uses let's say K CDs, and the optimal algorithm uses O1, O2 and so on up to let's say M CDs. So because we are assuming that optimal is better than the greedy solution, so it would be able to write all these songs in fewer number of CDs as compared to the greedy algorithm. Okay, so basically what that means is this M should be less than K. So this basically implies that B of OM is equal to N. So the highest song that is written in the mth CD by the optimal algorithm should be the last song, the nth song. And because k is greater than m, this means that the highest song that was written by the greedy algorithm in the mth cd, b of g of m, should be less than n. Okay, because the greedy algorithm is using more number of CDs as compared to the optimal algorithm. Now notice, this basically contradicts our hypothesis, right? We just proved that b of g of I should be greater than or equal to b of o of I for all I less than equal to k. Okay, so which means this is not possible, and which means basically this is not going to be possible. The optimal algorithm cannot beat the greedy algorithm, and greedy algorithm must be optimal. This basically brings us to an end of the review questions here. So I encourage you to solve these questions as many times as you can. In fact, I recommend my students to solve the review questions until you are able to solve all the questions without any assistance from the solutions. That is the best way to ensure that you have understood the questions thoroughly, and you would be able to apply similar concepts in the exam. After you do this, please also go through all the lecture slides, all your class notes, the homework assignments, questions in the homeworks. I have released the homework assignment solutions, and also complete any recommended readings from the textbook. I hope this discussion was helpful. Please let me know if you have any questions. So feel free to write to me or stop by my office hours whenever possible. Thank you.